In this video, I'm going to look at a quick nuclear decay simulation in Wolfram Cloud / Mathematica. So first I'm going to generate a list of ones, and one is going to represent an undecayed atom. So there's probably a different way to do this, but I'm familiar with RandomChoice, so I used it. RandomChoice takes a set of things. I only have one thing, the number 1, and then it's going to generate 100 of them. So that's not very random, but it was handy. I knew it. Okay. And then the next, I'm going to make an empty list, and I'm going to, this is the list for at each time step, I'm going to ask how many of the atoms are left, and then keep track of them in time. And that's what number left is for. So it's just at this stage, I haven't done the simulation yet, so it's an empty array, but as I go through my time steps, I will figure out how many are left and sort of append it to this list. Okay. Now comes the part with the actual simulation. So I have here a nested loop. So my outer loop, where my counter is t for time or time step, I'm going to go through 50 time steps. So I'm starting my counter for that loop with t equaling 1. And then my next argument in this for method is to the condition under which I continue to iterate, so long as t is less than or equal to 50. And then my third argument of this for function is how I'm going to increment this variable. I'm going to increment it by 1, so the shorthand t++. And then all the rest of this is the fourth argument of the outer for loop. So there's an outer for loop. It is in Mathematica a method. It has arguments. It has 4 arguments, and all of this is the fourth argument. So it's a very complicated fourth argument. And if you have multiple statements in here, they get separated by semicolons. So that is the outer loop. The first thing we do, the first statement of the outer loop, what we're going to, the statements we're going to execute is the inner loop, another loop. So again, we start with the for method. It's got 4 arguments. This time I'm going to count with a different counter, j, and I'm going over however many atoms. I'm looping over my atoms list. So they start counting at 1, so I initialize that counter to a 1. I'm going up to including the length of the atoms list, and I'm incrementing by 1s. So again, the for loop has 4 arguments. The first 3 are establishing the counting, and then the last argument is what I'm doing with the iterated step. So I'm starting at 1, I'm going up to the length of the atoms list, which was 100, but I wanted to make it generic, and I'm incrementing by 1, and I'm taking the jth element of my atoms list, which when I start, they're all 1s. They're either going to be 1s or 0s as we go. And then I'm going to multiply that. I have an if method. And in the if method, there are 3 arguments. The first one is a condition, and what you want to do if it's true, and what you want to do if it's false. So I'm just going to generate a random number with no other parameters. This generates a random number between 0 and 1. I'm going to ask if that's less than 0.05. If it is, I'm going to make the if a 0, otherwise I'm going to make it a 1, and then I'm going to multiply it by atoms j. So if atoms j was a 1, then I multiply it, and I got a number less than 0.05, then I would be multiplying it by 0, and I would get 0. Otherwise, I'm multiplying it by 1 and it stays 1. So Adams J, and then I'm multiplying that result by Adams J. So Adams J is then either going to be a 1 or a 0. Once it's a 0, it will stay a 0. And when it's a 1, it's got some probability of becoming a 0, some probability of the atom decaying. Again, 1 represents that it hasn't decayed, 0 represents that it has decayed. And then I make that the new jth element of the atoms array. So as for a given time step, I'm going through all my atoms, and if they are 1s, if they still exist, I'm giving them, there's the opportunity that they might decay. Okay. Now I'm done that's my step. That's the simulation step. Now I want to, at that step in time, record the results at that time for my simulation. I'm going to do that with a tuple. So I create an empty little list here. I decided to call it my tuple. I create an empty list and I add my time to it. And I take my atoms, which is my list of 0s and 1s, and I'm going to total it. So I'm going to add up the 1s and the 0s, effectively the 1s, and effectively the number of non-decayed atoms. And so then my tuple then has 2 parts, a time and a number left, and then I add my tuple to my overall results called number left. And here's the end of the outer for loop. And then when that's all done, I'm printing the number left list of tuples, times, and number left. So we see that in that time 1 of the 100, I started with 3 decayed and I was left with 97. Then in time 2, I had 91 left. At time 3, I had 90 left, etc. And that's the simulation. Now I'm just going to do some brief analysis of it. So first thing I want to do is plot it. We're expecting, if it's a nuclear decay simulation, some exponential decay. So I'm making a ListPlot, which plots data, which plots a list. I have these little tuples, so it's going to assume the first is an X and the other one a Y. I give it a label. I label the axes. And I also gave it a name of data plot. It also has a name of out4, but it will be more convenient later on in case somebody's following me and they've done different steps or made errors or not made the same errors I've made, then that this number could change. But if I name it, then I have more control over it. Okay. Now I'd like to fit it just to an exponential functions. So I'm defining, it's a pretty simple predefined function. I'm defining it as a function. So I have, I defined beyond just an exponential, I defined a function with 2 parameters and a variable, a coefficient, and what I'll call a factor, something that's inside the exponential. And now I'm going to take the data, number left, and fit it to this form. And then I specify in that form which ones are parameters and which is the variable. So the variable is X and the parameters are A and P. And then I'll just give it, put it in a ballpark so it doesn't go crazy on me. And I know that I started off with 100 at time equals 0. So my best guess for A is 100. And B, it's decaying. So it's some negative number. And I just put in negative 0.1 here. Okay, so now I called the result of the FindFit, I called it params, just to give it a name. And now I'm going to take my function that I defined and put the specific parameters for this in using this slash dot. So I'm going to substitute the parameters into this form. And so there are the specific numbers. So now I had my generic, I had my form, and then I got to use FindFit to find specific parameters. Now I put those parameters into my form. Okay. Now I'm going to, and I called it the fit. So now I can plot the fit, and I'm also giving that a result, calling it fit plot, and I'm plotting it from 0 to 50. I took in my simulation, as you recall, 50 steps. There is the fit. And now we're going to bring together the data and the fit and then display the equation. So I'm going to have an epilogue, an inset with the fit, and I'm going to position it at an X of 30 and a Y of 80. And there is my result. So that's what I wanted to show you. Just a bit of fun with Mathematica, doing a little nuclear decay simulation, playing around with tuples and lists and nested loops, and some fitting and plotting and combining list plots and all sorts of fun things. All right, thank you for your attention.